Hello everyone. This is a talk on interactive coding, and our main result today will concern how to construct interactive coding schemes that are both deterministic and efficient. I will start by defining what is a coding scheme, both in the interactive and the one-way setting, and then describe our main result and finish with an overview of the techniques. So let's start. One-way coding schemes are studied in the following two-party settings. There's a party Alice with a message M, and there's a party Bob, and Alice wants to send M to Bob. The reason this task is non-trivial is because the channel connecting Alice and Bob is noisy. And if Alice were to send M directly, then Bob will receive a message M prime different from M in a constant fraction, an adversarially chosen constant fraction of locations. So how does Alice send the message M to Bob? Well, the solution is well known, and it is to use error-correcting codes. Alice first takes her message M, encodes it to a code word C, and then sends C over the channel. The channel adds some noise to C, so an adversarially chosen constant fraction of locations in C are corrupted to get C prime. But regardless, this code word C prime still has enough information for Bob to recover M from it. Okay, so the task of sending the message M over a noisy channel reduces to the task of constructing good error-correcting codes. And by good here, I mean the following three properties. The error-correcting code should be deterministic, which means that the algorithms used by Alice to encode and the algorithm used by Bob to decode C prime are both deterministic. It should be efficient, which means that these two algorithms should run in time polynomial in the length of the input. And moreover, the code should be constant rate. And by this, I mean that the length of C is only a constant factor more than the length of M. We have codes with all these nice properties since a long time, and therefore we know how to send a message M over a noisy channel. Okay, so let us generalize this problem, and let us consider how to have a conversation that has many messages over a channel that is noisy. And actually, let us even consider the simple case where all of these messages are only 1 bit long. So you have many bits that Alice and Bob want to send. Alice will send the first bit over a noisy channel. Then Bob will send the second bit. Alice will send the third bit. And all of this communication should happen over a noisy channel. This setting was studied by Schulman in '92. And the question is the same. How do you make such a communication scheme resilient to the noise in the channel? Now, many schemes have been proposed starting from this paper in '92 itself. And those schemes can be roughly categorized into two different paradigms. The first paradigm uses the observation that if Alice were to know all the bits that it would send, so if Alice knew the first bit, the third bit, and all the odd bits that it would send over the channel, then Alice could just take all of these bits and encode them together using an error correcting code and send the encoding, just like a one-way channel. And Bob could do the same. So this observation implies that the challenge in interactive coding is the fact that these bits are revealed in an online manner. And what you actually need is an online variant of error correcting codes to perform interactive coding. This variant is called tree codes, defined first in '93. And tree codes imply interactive codes by the same argument as before. Okay, now, the thing with tree codes is that they are deterministic, which is nice, but all tree codes that have a constant rate are inefficient. We do not have, to date, any efficient construction of a deterministic tree code with constant rate. And therefore, all the interactive codes constructed on such tree codes are also inefficient. Okay, this is the first paradigm. What is the second paradigm? The second paradigm of interactive codes is based on the observation that in the interactive setting, Alice and Bob can detect whether or not an error happened in the following way. Suppose that Alice and Bob are running this noisy protocol, and at some point, Alice has some list of bits, a transcript of bits that she has sent, and Bob has a transcript of bits that he has received from the channel. Now, these parties can detect whether an error happened over the channel by just checking if the bits that were sent by Alice are the same as the bits that were received by Bob. And this can be done, for example, by just exchanging a random hash function of these two transcripts and seeing if they match. If they do match, then there are no errors. The transcripts are the same and the parties can continue the simulation. If they do not match, then there were an error and you need to rewind and try to fix the error. So this forms the second paradigm studied by Shulman in '92 and also by BK12 and many other words. And this paradigm uses hash functions, so it is randomized, but it is efficient because we have efficient constructions of hash functions. And the question we study in this paper is whether you can get the best of both worlds. Is it possible to have an interactive code that is both deterministic and efficient? And actually, this slide itself suggests two approaches for tackling this question. The first one is to try to construct tree codes that are efficient. So you want to attack this red here. And the second one, is to construct or to de-randomize these hash function based interactive codes from, say, BK12. Okay, so let's see these approaches one by one. The first approach is to construct tree codes that are efficiently encodable and decodable, and this would imply interactive coding. And this question has been studied since a long time, actually pretty much since Shulman's paper in the 90s. And the first construction was neither efficiently encodable nor efficiently decodable, but it had a constant slowdown or constant rate. Then in 2014, MS14 proposed a construction that was efficiently encodable, still not efficiently decodable, had a constant slowdown, but the proof of efficient encodability required or relied on a conjecture that is still open and has not been proven to date. So under this conjecture, they have a tree code that is constant rate, efficiently encodable, but not efficiently decodable. Very recently, in these two papers, we have a provable construction of tree codes that is efficiently encodable, still not decodable, but it has a slightly worse slowdown. The slowdown is doubly logarithmic in n, which is the length of the protocol that we are simulating. And the conclusion I want you to take from this slide is that there has been a lot of progress towards getting tree codes that are efficiently encodable, but the problem of getting tree codes that are efficiently decodable as well seems to be much harder. We do not have even like a conjectured candidate construction of tree code that is efficiently decodable. And this is where this approach is stuck. So our paper takes the other approach. Our paper takes the approach of de-randomizing the hash function based consistency checks in schemes like BK12. And can we do this? Well, we can do this. And our main result shows that yes. And formally, it says that if you have a tree code that is efficiently encodable, it may not be efficiently decodable, but such a tree code is enough to replace the hash functions in BK12 and get a deterministic interactive coding scheme that is also efficient. Okay, now as I said, we do have constructions of tree codes that are efficiently encodable, and plugging those tree codes into this main theorem also it gives new interactive coding schemes. For example, if you combine this log-log-n slowdown tree code with our theorem, then you get a deterministic and efficient interactive coding scheme with a log-log-n slowdown. You'd also combine, there are some technical conditions, but you could also combine the conjectured tree code from MS14 with an order 1 slowdown and get a deterministic and efficient interactive coding scheme under the same conjecture and also a constant slowdown, which would be the ideal. Okay, so this is the main result. And the rest of this talk, I will overview the techniques that go behind this result. I will first describe the BK12 interactive coding scheme with hash functions. Then I will show why tree codes are a good candidate to replace hash functions, but they do not work as is. You need to deal with several problems that I will talk about in the last section of my talk. So let's start. I want to cover the BK12 interactive coding scheme that had a hash function. And it will be helpful to just consider this interactive coding scheme on one interactive task, which is the pointer chasing task. This task is actually complete for all tasks, but we will not need those properties. We just define the task right away as a task defined on a binary tree of some depth, here 4. Alice has all the vertices that are red, which is all the vertices in all the odd layers of the tree, not counting the leaves. She has this root vertex, which is layer 1, and she has the 4 vertices in layer 3. Bob has all the vertices in all the even layers of the tree, which are marked blue. And out of every vertex that they have, Alice and Bob have a pointer to one of its children. This pointer points to a correct child or a correct edge from that vertex. And the task is to output the unique leaf that can be obtained by chasing all of these correct pointers. Okay, I claim that this task can be done in 4 bits if you don't have noise. And this is how. In the first round, Alice just sends the first pointer. She knows it. Then Bob is at this vertex and he sends this pointer. This again requires only 1 bit because you only need to indicate whether to go left or right. Then you're at this vertex. Then Alice will send the pointer from this vertex. Bob will send the pointer from this vertex, and you are at the correct leaf. The task is solved. If you have noise, however, then this protocol does not work. And for example, any one of the locations here can fail. For example, if the second locations fail, then you will have something like the first edge is received correctly. The second edge should have been this, but it was corrupted, so Alice got to this vertex instead. Then she sent the edge from this vertex, which Bob misinterpreted, and he reached here. And then both the players output an incorrect leaf. So this is what we want to correct. We want to correct the fact that the parties may be talking about different vertices during the protocol. And the BK12 coding scheme does that in the following manner. Again, you start from scratch, and at every point, you send the edge from the vertex together with a random hash function evaluated on the transcript we have seen so far. So in the first round, you will send the first edge. Now, Alice will say that she has seen this transcript. She will send a hash of this edge. Bob has received this directly, so he will also send a hash of this edge, and these hashes will match. This means that all is good, and they will continue the simulation. In the next round, Bob will send this edge. Alice will receive a corrupted edge, which is this one. This time, they are seeing different edges, so the hashes will not match with high probability, and they will detect this. Once they detect that the hashes do not match, they rewind. They go up 1 layer to this blue vertex, and then restart the simulation. This time, maybe there were no corruptions. So this time, both of them chase the same path and the hashes match. They go on, keep chasing the correct path. The hashes again match. And eventually, they reach the correct leaf and output it. So this is the BK12 interactive coding scheme. And observe that all we really used from the hash functions was that as soon as you have 2 transcripts that are different, then the hash functions can detect this disagreement with high probability. Can tree codes have an equivalent guarantee? Is it possible for tree codes to give a guarantee that looks something like this so that we can just plug it in directly and get a scheme that is deterministic, because tree codes are a deterministic object? Well, let's first see what tree codes are. A tree code, I want to think of as a binary tree, a possibly infinite binary tree, where each edge in the tree is labeled using a symbol from some alphabet sigma. For example, this edge has the label sigma 1, this edge has the label sigma 1, 0, and so on. And this labeling satisfies a distance guarantee, which is the following. Suppose you start from the root, and you look at all the labels on the path from the root to a vertex u and another vertex v. Now, these labels must be identical to the least common ancestor because the same path, there is the same path from u to v before the least common ancestor. But after the least common ancestor y, the labels from y to u differ from the labels from y to v in a large fraction, 0.9 fraction of all the locations. So if this location has length L, then 0.9 L of these labels here will differ from the corresponding labels from y to v. And this actually seems to be great. As soon as you have transcripts that are different, then in 0.9 fraction of the locations, you detect this disagreement by checking the labels. And maybe you can just plug this into the BK12 scheme and get a deterministic scheme. It's not that simple. This does not work. And the reason is that there is a subtle difference in the guarantee provided by the hash functions and tree codes. With a hash function, what you have is that for any 2 strings that are different, you detect this difference with a large constant probability. For tree codes, You do not get this guarantee for any two strings that are different. You only get this for 0.9 fraction, a fixed 0.9 fraction of the strings that are different will allow you to detect this difference using the tree toad. This means that there are unprotected regions in the tree toad. There is a region of length 0.1 L somewhere on this path, such that even though you are in different locations on the tree toad symbols will not protect you. The tree toad symbols will still be the same, and you will not detect this disagreement. And these are a real problem, because what may happen is that you may have an interactive coding scheme that starts from R, then the adversary invests a lot of corruptions, and it takes you inside this unprotected region that is shaded red. Now, when you're inside, the tree toad does not protect you, so without any corruptions, you go all the way to the end of this region. And it is only here at the end of this region that you detect that there was a problem. Now, you detected this problem, so you rewound. But hey, you only rewound to a place inside the unprotected region. And again, you will not detect that there's still a problem till you go back down to the end of the region. And what will happen is you'll keep looping around up and down this unprotected region. Sorry about that. Without making any real progress. You'll never escape this unprotected region. And this brings me to the last section of my talk, where I will describe the ideas that go behind. This is actually the crux of the ideas in the paper that go behind escaping the unprotected region with only a constant overhead. So let's see this. This is our problem. We have a path from R to U, a path from R to V. The adversary has brought us inside an unprotected region, and we want to escape it. Our first idea uses the observation that any such unprotected region is actually due to an error at the beginning. There was an error at this point Y in the simulation that caused Alice and Bob to go on two different paths, and now they're inside this unprotected region. So what we want to do is we want to, when we detect this error at the end of the region, we want to go back up all the way to Y, where this error happened, and rewind all the way to Y, and then continue simulation from there. This is the ideal execution. If you rewind all the way to Y, you have corrected all the errors. And when you continue the simulation, you have a fresh tree toad that will protect you throughout. Okay, the way we do this is by using a backwards tree toad. While we are rewinding, we don't rewind only a constant number of steps. We'll keep rewinding till we find this error. We keep rewinding till the symbols that we rewind are different for Alice and Bob. There will be a point where the symbols are different because this point Y is one such point. And we will keep rewinding till we hit the first point where the symbols are different. And this is done using another tree toad, but this time in the backwards direction. So it's a backwards tree toad. But this does not fully fix the problem. The reason it does not fully fix the problem is because there may be multiple errors on the path from Y to the unprotected region. In particular, there may be an error here at Y, which caused the parties to diverge. And there may be another error very near to the beginning of the unprotected region. And in this case, when you start rewinding from the end of the unprotected region, you detect the second error that was here at the beginning. And once you detect this error, you think that this is the point Y, and you start going forwards from this point. But this wasn't actually the point Y. This was the point actually very close to the beginning of the unprotected region. So the adversary can do something like this. He can reinvest this error when you start going forwards and bring you to the same unprotected region that you were in before. Again, you will not detect it till you reach the end of the region. And again, when you detect it, you will go back to this point, and then you will loop around now inside this unprotected region at the cost of only a few corruptions, which is this one error that will invest every time you reach the top. Okay, so this is still not done, but we can fix this. And we can fix this by adding a patching forward tree toad. What this tree toad does is when you detect an error at the end of an unprotected region, and you go back to find the first point of discrepancy, and you start resimulating the protocol from this point, you don't just do it on the original tree toad. You actually add a second tree toad to your system, and send encodings on both the tree toads. Now, because you have two tree toads and you're sending encodings on two tree toads, an unprotected region must be unprotected on both the tree toads. In particular, this red region is not an unprotected region anymore because it is protected by the second tree toad. So now when you go forwards, you will detect errors fast and you will go back up and maybe you go back up to Y very fast. This is the hope. But again, this does not happen. But before I describe why it does not happen, let me point out a feature that I did not mention, which is that it does not stop at two tree toads. Just like there were regions that were unprotected for one tree toad, even if you have two tree toads, there will be regions that are unprotected for both the tree toads. And the adversary can do this attack in those regions when you will need to add a third tree toad. And this will not stop anywhere. You can have an arbitrarily large number of tree toads that you're carrying with you, and you're sending, you're encoding different parts of your transcript using all these different tree toads. So this fix actually induces a lot of complications where you need to control when you add tree toads to the stat, you need to control how many tree toads are there in your stat. You need to control when to remove tree toads from the stat because each tree toad costs you something in communication. And there are several complications that arise from carrying several tree toads. But even with this stat of tree toads, you do not have a complete fix. And what is the problem now is the fact that you may have many errors from, and not just two, from Y to U and V. Let us see what happens when you have one error at Y and then you have several errors before the unprotected region. In this case, when with all these errors, the adversary brings you inside the unprotected region, you detect these errors at V, you go back up, you find the first error, and you start a new tree toad that will protect you from this point onwards. Now, this tree toad does protect you from this error in the future, but this tree toad does not offer any protection from all the errors that happened before it. So the three errors that happened before the point this tree toad was inserted are still not being protected against in this red region. And what may happen is that you do not insert any corruptions on the new tree toad, but when you reach this bottom point, you still haven't detected these three errors because these were unprotected. Now you'll detect the last one of these three errors and go back up to that point. And then again, you'll add a new tree toad to fix this problem, but this again will not protect you from the two errors before it. So you will do this, you'll fix one more error. And if this whole region was of length L, then you will need L square such steps each time you fix one more error to get out of this unprotected region. If L can be as large as the length of the protocol, and therefore this is a quadratic overhead and not a constant overhead. Okay. The fix around this problem is to double the backwards tree toads. What do I mean by that? Well, when you detect an error here, when you detect the first error, you don't stop going backwards and you don't immediately start a patching tree toad. What you do is you double the backwards process. You go back double of what you've already gone and start the patching tree toad from there. Now, because you're doubling each time, you're correcting more than, you're not only correcting the error you found, you're also correcting all the errors that were close to it. And actually, this doubling process will converge linearly. So the question to ask is, does this doubling fix it? The answer is still no. And the reason is that just like you had to double the backwards tree toads, you also will need to double the patching tree toads for an attack similar to the one I described. And moreover, you will need each successive tree toad that you use in your stat to be more and more secure. It should have a better parameters so that you have more security. But when you do all of these 6 steps, you do get a scheme that will escape the unprotected region with only a constant overhead. And you can plug it into the BK12 interactive coding scheme that uses hash functions to get an interactive coding scheme that is deterministic, efficient, and only assumes efficient encodability of tree toads, not decodability of tree toads. With this, I finished this talk. Thanks for listening.